Measurement of low pressure and gas flow in coating deposition system. Today we shall discuss this topic. Now we must find out the significance of pressure measurement during this coating deposition. Point number 1 is that before conducting this deposition, the deposition chamber in most of the cases need to be pre-evacuated down to 10 to the power minus 5 torr or even better to remove the traces of oxygen and other contaminating material to have effective deposition. And during the deposition, what is important to monitor and to measure the pressure and to have a proper control on this pressure, because in the outcome of the quality of coating it is observed that this pressure has a very significant influence on the quality of coating. Mostly it is the structure of the coating, then the density of the coating, porosity, and in certain cases also the growth rate. Sometimes it is also seen that the composition of the coating is also altered by this pressure. So, in summary, what we can say that during this deposition the pressure has to be monitored, and before start of the coating process in many cases it has to be evacuated to a very low value of pressure, that means a very high vacuum. Now here it is important to know how to have full assessment of this process, that means measurement of the low pressure, that means evacuation of the system, how effective the pumping system is and how quickly it can pump down to that low pressure, and for that we need some sensing element to measure that low pressure. And also during the deposition, when the pressure is relatively high, that monitoring is also necessary. And in many PVD system, what we have, one roughing line and one is the backing line, that means roughing evacuation to a very not to very low value and followed by which is further refined, that means evacuation is carried out down to a very low value of pressure. So, in both the cases we need a sensing element for measurement and control of both this of the pressure. Now here what we can see that measurement of the pressure, it can be done by direct measurement or by indirect measurement. Direct measurement, what we mean that in this case the deflection of any mechanical part component can be translated into the difference, the fall of the pressure or in the change of the pressure. What we mean here, because of the change of pressure in the system, there will be some mechanical displacement or deformation of any mechanical element, and that can show that fall of the pressure or change of the pressure, and this is what we mean direct measurement. And there is some indirect measurement which we shall cover. That means because of the change of the pressure, some other characteristics of the gaseous element which is present, it changes its characteristics, and which is a true reflection of this change of the pressure, and thereby this indirect measurement can also be true representative of this change of the pressure. Now, here we see that the very basic and very fundamental Bourdon vacuum gauge, and schematically we can show this thing. This is nothing but a tube, a circular tube which is originally circular, but it is made something like an elliptical tube in this shape, elliptical tube, and this tube changes its shape and dimension when some change in pressure occurs within this tube. It can be a fall of pressure or it can be rise of pressure. Now, it is basically an elliptical tube, and we shall see how does it work. And when this elliptical tube is submitted to high pressure, then this dimension changes and it becomes more circular in nature. That means this major axis and minor axis, that difference will be further narrowed. However, when it is subjected to high vacuum, then it will be flattened and this elliptical shape will change more or less of this shape, and then also we have some change in the dimension. So, this ellipse will either move towards more of a circular form or it will get the shape of a flattened shape what I mean, and in that case also there will be some change in dimension. And what exactly it means we can see quickly here schematically. This is a tube, and let us draw this tube like this, and it is of almost 270-degree bend. So, this is the tube, and at the end what we have here centrally we have one needle, and this needle is actually fixed with one pinion which is nothing but a toothed wheel, and here we have the pointer, and it can work over a scale, and this will be in mesh with one sector gear like this, which is having also teeth, and there we have one extension of this lever, and here we have a pivot. So, what happens as it moves on this side, this sector which is pivoted at this point, then this sector, tooth sector will move this thing, and then this pointer will move about this axis, and here if we have the graduation, it can show the pressure. So, it is the graduation. Now, what happens? This is actually, this is connected to the vacuum, to the chamber, to vacuum chamber. And this side which is actually soldered, and here we have a rigid link. So, this is a rigid link, this side is closed. So, the tube is opened only on to this vacuum chamber. Now, what happens as we evacuate the whole system which is on this side, then this tube will get flattened from this elliptical shape, it will get flattened, and then it will bend more towards the center, it will not open up. When it is high pressure, then it will open up, but now it will bend more towards this side, and as a result of this, this will move, this will push this thing on this direction. So, this is actually moving in this direction, and as a result this sector gear which is pivoted at this point, this end will be pushed on this side because of this bending of this tube, and then this sector will have a rotation, and this rotation will be transmitted to this pinion which is actually rigidly holding that pointer, and this pointer will move this way, and that will show the fall of pressure. And when we increase the pressure, then it will move this way, and then this tube will try to open up with high pressure, and because of the high pressure this link will be driven on this side, and then this will move like this, and as a result of that this will simply indicate high pressure. So, this Borden vacuum gauge basically it is used for a comparison and quick assessment of the pressure, and that can be sometimes quite convenient to work with. Now, this principle of mechanical measurement of the pressure by direct coupling of this mechanical system with a vacuum chamber, that can be further extended in the form of a vacuum diaphragm gauge. So, it is actually a diaphragm gauge, and in the diaphragm gauge what we have? We have actually a chamber like this. So, a chamber is actually divided into two compartments, and this side is connected to the vacuum system, that means which is the coating system. So, this side actually it is vacuum chamber, and the construction is such that this side is actually pre-evacuated during the construction of the gauge. This is actually evacuated to 10 to the power minus 3 torr. And here what we have? We have here a shaft which is actually fixed to this diaphragm, and here we have the bellow. So, it is flexible, and on this top of that what we have? We have a string. We have a string, and then this string passes over a pulley, and then this is actually under tension with the help of a spring. Now, this pulley will move up and down depending upon the pressure what is prevailing in this vacuum chamber. Now, if it is 10 to the power minus 3, when it is a high pressure, suppose now the vacuum chamber is filled with air, and in that case this will be 760 torr, which is higher than 1 minus 10 to the power minus 3 torr. So, naturally the diaphragm will have a tendency to move in this way, and this way the whole shaft, this string and the pulley will move, and there if we have a pointer, then this pointer will move on this on a scale, and this side movement on towards the right mean high pressure. High pressure. However, when we evacuate the system, I mean down to about 10 to the power minus 3 torr, and this is actually a gauge which is used for measurement of low vacuum. Low vacuum, that means high, not too high vacuum of the order of 1 into 10 to the power minus 3 torr. In that case, what is going to happen when we evacuate the system? This diaphragm which is already bent, that will try to restore to its original position. So, that means the whole thing will move in the downward direction. So, the string will be pulled and it will be under tension. So, as a result of that, this pulley will move, because the string is passing over this pulley, and that is why this gauge will move and the pointer will move in this direction, which also indicate low pressure. So, this Borden tube, which is a deformation of the elliptical tube, which becomes more and more flat, that can be also used for measurement of the pressure, or here it is the diaphragm gauge. Diaphragm gauge which can be also used for measurement of the pressure, and however, it can be noted that this pressure is only limited to 1 into 10 to the power minus 3 torr. Now, this can be further extended. Here what we measure the mechanical displacement of some of the mechanical element, and in this case this element is a diaphragm, a shaft, the string, the pulley and the pointer. But this can be also transformed, little bit modified, and that can be converted into a capacitance gauge. So, it will be more or less similar to this one with little modification. That means, in this case what we have here, we have one capacitor, one plate of the capacitor, and this side what we have, this is going to be actually so this is another plate and which is fixed on this side. So, these are the two, this is one plate and this is another plate of the capacitor, and on this side we have the this Wheatstone bridge. Wheatstone bridge for the capacitor, and this side actually it is connected to the vacuum chamber. So, what happens during evacuation, this diaphragm will change its shape or position when it is evacuated. So, depending upon the rise of pressure or the fall of pressure, what is going to happen, this diaphragm will change its position, and since this plate of the capacitor, the upper plate of the capacitor, it is rigidly connected with this diaphragm. So, naturally this gap, the space between the plates, that will keep on changing, and that will change the capacitance of this capacitor. And on a Wheatstone bridge, one of the arm, if this becomes this capacitor, then its capacitance will change, and that will generate one error voltage, and this Wheatstone bridge will give some output, and this output will have a relation with this pressure which will be prevailing in the vacuum chamber. So, this side is the vacuum chamber, evacuation of the chamber or backfilling with the chamber, and as a result the change in dimension and position of this diaphragm, and this diaphragm is rigidly holding this plate. So, this plate will change its position, but this is rigidly held, and as a result of this displacement of the capacitor, capacitance plate, that is actually converted into the capacitance, and it is an indirect measurement, and this is not a direct measurement what we have described in this diaphragm gauge. So, this capacitance gauge is also used in the order of 10 to the power minus torr, and since it generates one electrical signal, this can be also used for feeding this error signal to the downstream side of a evacuation chamber, or during the deposition to monitor the opening of the valve which is controlling the pressure. That means, what I mean, that if we have a preset value, and if there be any deviation from this value, and that will be recorded here, and that error signal will be fed, this output will be fed to the motor driving this throttle valve. It is actually setting the position of the throttle valve, and that throttle valve will have its a particular position to restore the pressure. So, this kind of capacitive gauge will be essential for control of the pressure, a particular value, or setting any value. It is very convenient way of handling this kind of particular problem. So, this is actually the type of gauge where we use mostly the displacement, or say the deformation of one of the mechanical element for measurement of the pressure, and this is the pressure within the coating chamber. However, we can have also diaphragm gauge, capacitance gauge, that we have mentioned here, and now comes thermal conductivity gauge. This is also used in the range of say 760, that means torr, 760 torr or 1000 millibar, 1000 millibar. So, from this to 1 into 10 to the power minus 3 torr. So, that is the pressure range within which this thermal conductivity gauge can work. Now, the basic idea here is that this thermal conductivity of a gas does not affect is not affected by the pressure when it is above 10 torr. It is also known in the theory, but when it is below this pressure, then its thermal conductivity thermal conductivity is affected by the pressure. That means, the change in pressure can have a direct effect on this thermal conductivity of the gas, and accordingly this heating or cooling effect will be affected, and this is kind of indirect measurement. Actually, the heat loss of a heating element, when the heating element is hot and because of some conductivity of the medium, some heat will be taken away, and in this case a heating element is put inside the gauge, and this, when it is centrally placed, we can illustrate here, and this is centrally placed, and when it is hot, this gas molecules can take away the heat just by conduction, and when it hits the wall of the gauge, then this heat is transferred on this wall. Now, the number of molecules available within the gauge, that also depends upon the pressure. Lower the pressure, less number of molecules available for this heat conduction, higher the pressure, more number of molecules available. So, cooling is, that means heat conduction is more, and less the pressure, heat conduction is less. So, there is one equation, and what can be written as E k, that means the heat loss due to this conductivity, it is given by alpha by 2 minus alpha root over into So, here we find that this is called accommodation coefficient, this is the molecular thermal conductivity, prevailing pressure, this is the temperature, and this is the room temperature. And here what we find, that lower the thermal conductivity, molecular thermal conductivity, less will be the heat conducted by the gas. Now, this guiding equation is well utilized in construction of a gauge which is based on this thermal conductivity principle, and one of such is Pirani gauge. And in this Pirani gauge, what we see, that it is basically a heating coil, and this is supported on a stand, and this is one 2 terminal, and the whole thing is encased in a container, and this side is the opening, and so this side can be connected with one port of this vacuum chamber. So, this side will be connected to this vacuum chamber. So, basically here we have one heating coil, and this may be made of, say for example, tungsten, and this side is a metal support. So, these are the 2 terminals. Now, what is added to this? It is basically a Wheatstone bridge. So, this is one resistance, and then what we have, this one should be placed like this. So, this constitutes one arm of this Wheatstone bridge, and then we have another arm, and that is the closing arm. So, here we have, this is say resistance R1, and this is going to be the resistance like this, which is connected to this vacuum chamber. So, this is the vacuum chamber. So, this is RP, say for example, and this is R3 and R4. Now, and here what we have additionally, this is the input to this bridge, and that is going to be the output of the bridge, and we are interested in this. What is the output of this bridge because of this change of pressure? Now, what is going to happen? We can write further to this, that in the null condition R1 R3 is equal to Rp into R4. Now, so long there is a balance, there will be no signal, and now this Rp is going to change. And how it is going to change? Because of this conductivity, fall of the conductivity because of the change in pressure, what is going to happen? The temperature will rise here, and this rise of temperature will cause a rise in the resistance, and this resistance will be, the value will be disturbed, and it will be different from the resistance what is actually prevailing during this null condition. So, as a result of that, we can have a output. So, that means the basically the resistance of this arm is changing because for a constant heat, the resistance of this one will keep on changing because of the lowering of the pressure and lowering of the thermal conductivity. And as a result, what we get? We get one output. That means this can be illustrated conveniently in a graph. So, say this is actually this meter reading. This is the meter reading, and with this meter reading, that is the output, and because of the change of pressure, and this change of pressure, we say this is the pressure and this is the meter reading. Say this is a milliampere. So, what we see, because of the fall of pressure there is change in resistance. So, what we can have? So, this bridge may be balanced in the atmospheric pressures. This is 760 torr. So, at the 760 torr it is balanced. So, signal is 0, and when it is about 10 to the power minus 3 torr, that is the limit, and here we have a full scale reading. So, this is the full scale reading. So, the graph may be like this, and that is the milliampere output from this this one which we can see again. So, this is actually the output of the bridge. So, this is the milliampere, and this milliampere is shown here with this, or it can be other way we can do, that is as a second option, that this milliampere reading from this galvanometer. So, bridge can be balanced at 1 into 10 to the power minus 3 torr, and it can have a full scale reading here. So, at 760 also we can have such highest possible signal. So, this way also we can see. In fact, the resistance Rp of this gauge, Pirani gauge, that increases with pressure because of the simple reason that here cooling effect is less. So, resistance will be heated, and as a result this resistance value will keep on increasing, and that helps in getting this error signal. So, this is one way of measuring, indirect measurement of the pressure, and that is conveniently used as a routine thing in any vacuum system for roughing the vacuum. That means, after loading this chamber, the pressure inside the chamber is at 760, 1 atmosphere, and when we run these vane pumps, all roughing pumps, so it is actually from 760 to a pressure say 1 into 10 to the power minus 2 and 1 into 10 to the power minus 3. In between we can reasonably attain the pressure, and there this pressure is actually registered by this milliampere reading on the meter. So, this way also we can have a thermocouple gauge. It is also the principle, basic principle is same. So, here we have one thermocouple, one heating coil, and this heating coil is actually there is a power supply, and centrally what we have a thermocouple at the exactly at the mid section. So, this thermocouple has two terminals. In fact, what we have here, this is the casing and here this is the opening. So, this side it can be conveniently connected to this vacuum chamber with this flanges, and here we have 4 terminals. So, this terminal will be the power supply terminal. So, here what we can do, we can change the power supply, and here perhaps we have 1 meter, and this is millivolt. So, this is volt, and here what we can see, that will be the reading because of this thermocouple, and that may be millivolt thermo EMF which can be generated. So, basically it is a heating coil which will be heated, and we give here a fixed power. So, this is actually thermocouple gauge, and this is the thermocouple, and here we have a millivolt to record the thermo EMF. So, now with a constant heating here, with a constant heating, and because of the evacuation change in pressure, naturally the heating effect will be more, because it will be more hot. If we have more of air, then the temperature will fall. So, depending upon the temperature, the EMF will be recorded, and this will be a true reflection of the pressure which will be on this side. So, that is actually the vacuum chamber. So, this way also we can have such kind of calibration, and this way we can see that this millivolt and this pressure. So, as the pressure is reduced, we can see more of this millivolt, because the loss of pressure, fall of pressure means higher the temperature, and there will be this junction will record higher thermo EMF, and that will be recorded. So, it needs calibration. So, pressure and millivolt reading that can be conveniently used for indirect measurement of this kind of thing, and this can be well used for measurement of pressure in the range of say from 760 torr to 1 into 10 to the power minus 3 torr. So, this is thermocouple gauge what we have mentioned, and now comes ionization gauge, and this ionization gauges are used particularly for a pressure of say 1 into 10 to the power minus 3 broadly to say 1 into 10 to the power minus 5 or 1 into 10 to the power minus 6 torr, where most of the vacuum system or coating deposition system for this mechanical application or wear resistant coating, thermal barrier coating, those are deposited, and that is the zone where normally the preparation work and the conduction of the coating process is done. So, this is the pressure, and here what we find that to record the pressure, that means evacuation of the system to this pressure, we must need a very reliable system, and for that what we have here this ionization gauge, where this ion current versus the residual pressure, that will be recorded, and that will be reliably used as a measure of pressure. That means, inside the gauge what we have in principle, we have one cathode and anode, and this will be used for ionization of the residual gas, and this ion current will be registered, and this ion current will be a reflection of the residual pressure. Let us have a quick look how does it work. So, basically here what we have, let us have a cross sectional view, this so this is just like an envelope, and what we have here, we have one we have one spiral. So, this has one terminal, this one too, and what we have in additionally here one electron emitter. So, this is the electron emitter. So, here we have 4 terminals and the whole thing is put inside a casing. So, this is the casing and outside what we have. So, this is this side goes to this is the flange and this side goes with this O-ring, it goes to the chamber. Now, what happens? We can also have another diagram for understanding, and this is like this here. This is the casing and then this is a plate what we call as an ion collector. So, this plate is the ion collector and so this plate is shown by this blue line, and in the central position what we have this one which we have drawn with the form of a helix. It is something like this in between and this is actually the electron collector. So, this helix spiral, this shape part, that is the electron collector and this is the ion collector, and this black one, that is actually the electron emitter. So, it is some sort of this thing, and here what we have, here we have emitter, in fact, this is also, here we can see that this I p, we can write it just like 273 by T into P r into P into I e. That means, this is one equation which correlates the ion current with electron current, and that is the inside pressure, that is the temperature, and this one is called ionization probability, and with this, in this principle this instrument works. So, what happens? This is electron emitter and with this residual gas. So, this is actually ion current and this is electron current. Ion current and electron current, and what we see here, that as this electron emits, it will be moved towards this positively biased collector which is in the form of helix, but if it does not, it is like a ring. If it misses, if it is not collected, then it will move towards this side which is negatively biased, but it will be repelled. So, unless it is collected by this grid which is in the form of a helix, it will have an oscillating motion in between, and this oscillation we can also show this way. So, this is the and here we what we have electron collector, and from here it is emitted, and if it is not collected here, it will move like this, it will go to this side which is negatively biased. That means, this is actually the ion collector. So, it will repel and it will move like this and this way. So, this way it will have an oscillation and finally, it will be collected by this electron collector which is positively. So, this is electron emitter and that is ion collector, and this is electron collector. So, if electron collector fails to collect, this electron will keep on swinging and it is having an oscillation. The advantage here is that this oscillation will actually facilitate collision, more collision with the neutrals and breaking up one positively charged ion, and this positively charged ion, release of this ion and collection of this ion, that will be indicated by this meter, and that is actually the measure of this ion current, and this is connected with the pressure, and as a result of this we can see that this pressure and this ion current, they are correlated. However, this is hot cathode ionization gauge. Though it is working and it can be used, one disadvantage of this one is that in the residual gas, if we have something strong contaminant or some reactive gas, that can also chemically damage or attack this filament, and life of the filament will be shortened. So, that is why this hot cathode ionization gauge is replaced by one what is called cold cathode ionization gauge. So, this cold cathode ionization, we do not have any heater, but there is one cathode plate we have in fact. So, this is actually hot cathode ionization gauge, but now we have cold cathode ionization. So, with this cold cathode ionization, what we see, we have in fact two plates. These are the two plates, these are the twin cathode, and centrally located one ring, and what we have further to this, this is the opening of this gauge. So, we have a connection like this. So, this should be positively connected, and these are, and here the field is about 4 to 6 kilovolt, very high voltage, and with that we can have extraction of these electrons from this cathode surface, and this will keep on swinging in between, and finally it will ionize unless it is strapped by this ring, like a ring anode, and it will keep on swinging, and this oscillation may lead to facilitate that splitting, having a collision with the neutral. And to augment this process, what we have here, the magnets. Two magnets are placed, and there we have the lines of force, and we have both electric field and the magnetic field, and as a result of this, the trajectory of the electron will be like a helical path, and with this helix it will have an oscillation movement. So, by this we are increasing the chance of probability, or increasing the probability of collision of this electron with this neutral, and thereby making this gauge is more effective by this augmentation with the magnetic field. So, this way this cold cathode ionization is used, and this is actually known as penning gauge. This is used for measurement of the pressure in the order of 1 into 10 to the power minus 5 to minus 6, and by this ionization current, and this ionization current is a reflection of the residual pressure. However, it may so happen that if we activate the gauge when the pressure is almost very low, in that case activation of the gauge may be little difficult. So, in that case what we have, one auxiliary emitter of electron which is activated to release additional electron, and once these electrons are in action, then this auxiliary emitter is switched off, and this is actually known as trigger ionization gauge. So, that is the triggering of this emitter which supplies additional electron at the moment when it is needed, and this may be useful when we like to switch on this gauge at the moment where the pressure is already very low. Now, we have another called, this is inverted magnetron gauge. Magnetron. So, here we also use one magnetron to augment this process of ionization and to make this gauge very effective during the working. That means, here we have one central anode, and then we have one annular cathode, and we have also one auxiliary cathode. So, these are the two cathode. So, this is connected to negative, so to positive, and this is to this is actually grounded. So, this side is positive. So, it is a power supply, and this side is grounded, and this cathode is actually grounded. So, here what we see, that this anode plate that is positively biased, and this cathode which is an annular, having an annular shape. So, this is grounded. And what we have in addition to this, we have the magnets, and with these magnets what we have here, we have the magnets. So, naturally this is north south. So, with this magnet we have a lines of force, and so we have this lines of force which is closing itself. So, this is the lines of force, and here we have one electric field. So, this is magnetic lines of force, and this is the electric field, and with this EB we have a drift motion like this. So, this is EB drift, and as a result, and if we see from the top, so thereby what we can see, if it is the cathode, on this cathode surface, what we can see, we can have the trajectory of the electron which will move like this. That means, basically the whole idea of this using this magnetron is to augment this ionization efficiency. That means, efficiency of this electron to make more ionization, meaningful ionization. That means, each electrons becomes more and more efficient, and when they are confined and localized and locked in a particular orbit, and this is already a drift motion, and this electron will have one orbiting motion, and further to this, because of this electron, this E and B, that means this electric field and the magnetic field, because of this EB drift, we have a drift motion. So, it is clockwise. So, naturally this will go this way. So, along with this circular motion, it has a cycloidal motion. That means, its path is longer, and these electrons are more efficient in that it has a longer path, and in this longer path, it has a fair chance of hitting one neutral and ionizing one neutral even with low pressure. So, with this magnetron, this is called inverted magnetron, because of the reason that here this is actually positively polarized and cathode is grounded, and this inverted magnetron type gauge is also used for very low pressure measurement. Now comes so inverted magnetron gauge that we have mentioned, and now comes this gas flow measurement. In fact, in coating deposition, we have two process parameters, basically the pressure of the gas, partial pressure of each gas and the total pressure. Both are important in monitoring the quality of the coating, composition of the coating, structure of the coating, stoichiometry of the coating, and also the amount of gas which is flowing per unit time. That is also useful in that the growth rate of the coating, then the amount, the number of parts which can be deposited, which can be coated, that also decides what should be the flow rate and the flow ratio. So, individual flow rate and the flow ratio all are important, particularly in all PVD, CVD coating, that individual flow ratio, individual flow rate and the relative flow ratio all are important, and in this case this measurement of flow and setting the value of flow is becoming also equally important. So, it is called a rotameter. Rotameter, actually flow measurement, fluid flow measurement or gas flow measurement, we have various meters, say orifice meter, venturi meter, something like that. But here what we see, it is called a variable area meter. So, it is a tube, it is a tube, and this is a taper tube. This is a taper tube, and here this is the input, this is the inlet, and that is the actually outlet. So, what happens? We have a ball, and the ball diameter, it is a floating ball, ball diameter matches with the inlet diameter. Now, what happens during the flow, because of the drag force and buoyant force, this ball will be floating, say here, and we have a scale. So, this height can be measured. So, on one side we have weight of the ball, and on the other side we have this buoyant force and the drag force because of this movement of this gas, and both are balancing each other, and this volume rate of flow, which can be liter per minute or liter per second, and that should be proportional. So, this volume rate of flow that is actually constant, a constant into height, and that is the principle of measurement. So, this ball has a weight, this is calibrated, and depending upon the height, which is calibrated in liter per minute, and under a particular pressure, this ball position shows directly the reading. Now, to increase the range of working, we can have 3 balls. For example, one made of Pyrex, the second one made of stainless steel. We can still use one heavy ball made of tantalum. So, having 3 balls here, we can have one which goes to the other side of the scale, but then the heavy ball may occupy an intermediate position. So, in that case, this heavy ball, or which is the stainless steel, I mean the density wise it is in between the pyrex and the tantalum, those can be conveniently used to measure the flow rate, and this is actually rotameter, and since it is also keep on rotating because of the gas flow. So, this is that is why it is called the rotameter. So, it is basically a float which will keep on floating under the action of the viscous flow and the buoyant force and the weight, and accordingly this annular passage will keep on increasing and the flow rate will keep on increasing. Now comes the mass flow controller. So, this is actually the mass flow controller which controls the amount of mass which is admitted. Basically here what we have, the construction is like this. This is a tube, inlet down upstream, and this is downstream. So, this is actually called sensing tube. This is sensing tube and this is bypass tube. So, what we have reasonably here, two coils, heating coils, it is actually like the resistance thermometer coil. So, these are constitutes two arm of a Wheatstone bridge. Now, what happens? It is actually the heat capacity of the gas that is utilized to record and to measure the flow rate. So, the arrangement is such that this sensing, the flow through the sensing line is proportional to the total flow, the way it is designed. The bypass line and the sensing lines are designed in such a manner that the total flow rate is proportional to the flow which is channelized through this sensing tube. Now, what happens when there is no flow? When there is no flow, these are all heated. Now, when there is no flow, when there is no flow, what happens? We have a temperature profile which is something of this sort. So, here mean value of the temperature in this zone and in this zone, they are more or less same, and these two being the two arm of a Wheatstone bridge, their resistance are R and R when there is no flow. However, when the flow is on, switch on, what is going to happen, that because of this heat capacity, that heat will be transported. That means, in this case the heat will be taken by this flowing gas from this heating element and that will be delivered on this side. So, that means, in this case when the flow is on, this temperature profile will change its location and it will go more, will be shifted towards this downstream side, and when this which is shown by black, that is no more in existence and it is more of a blue. In that case what we find, the mean temperature here is low and on this side it is high. Though naturally what is going to happen, here we have, because of this change in temperature, we have some change in resistance which will be shifted little offset from this null condition. So, this change of resistance will be less, that means it is minus delta R, and since heat is transported, heat is taken away and added on this side, we have the resistance which will be increased by delta R. So, this way what we can see, that this minus delta R and plus delta R. So, in the Wheatstone bridge arm there is a disbalance. So, there is a disbalance, and as a result of that what we see, that this does not there is a signal, and with this signal we can reasonably measure this particular flow during this process. So, it is actually change of resistance, and by this we can have a signal and which can be utilized for this measurement of the flow. and this way we can have a further understanding of both of pressure measurement device, both for low pressure and high pressure, low vacuum and high vacuum, and also the flow measurement.